Good day, everybody, and welcome to the OptiFDTD Introduction webinar. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host, Damien Merrick. Before we begin, I'd like to review the layout of today's webinar. So during the presentation, we will launch 3 polls, such as the one that you're looking at now. Each poll provides Damien with helpful feedback for guiding the presentation, so your participation in the polls is greatly appreciated. As some of you have seen, we'll be giving away a $50 Amazon.com gift card at the end of each session. To qualify for the draw, you need to be present for all 3 polls, so we're going to be taking attendance, and if you stay basically for the entirety of the presentation, you'll be put in for the draw. The winner for each draw will be randomly selected at the end of the presentation. And will be posted on our website approximately 30 minutes after the webinar completes. So this will be the same page that you originally signed up for. You'll see the list of qualified users and the winner of each session. And we're also going to handle questions at 2 different time intervals today. We're going to handle it at the halfway point and at the end of the session. Since we have a packed house today, we won't be handling questions via the raised hand option. So please type all your questions into the questions section only. You'll find this section in your GoToWebinar control panel. And in case where you'd like to keep your question completely private, you can send an email to support@optiwave.com and we'll answer it afterwards and just reply to you directly. If for some reason we can't answer some of the questions that you posted in the GoToWebinar control panel, we'll jot it down and reply to you afterwards via email as well. There's one attachment that you'll see in the control panel that you can go ahead and download at any time. It's a PowerPoint presentation. And lastly, we're going to be recording the webinar and distributing it to all registrants via a download link that you'll receive in an email tomorrow at this exact same time. In order to access the recording, you're going to need your same name and email that you used when registering for the webinar. So without further ado, I'd like to introduce your presenter, Senior Photonics Application Engineer, Damien Merrick.
Hi, hello, and thanks for the introduction. Let me just set up my share screen here and wait to make sure that everything is working properly. Looks like it is. So officially welcome to the webinar. This is an introductory webinar on the FDTD software. We have OptiFDTD, and as well as it's going to be a pretty good introduction to the FDTD method. So I'm glad to see that a lot of you answered in the poll that you have some experience, but maybe you're not very experienced, or you're not, I guess, experts in this field. I think this is a good presentation then, because I think a lot of users seeing the method's not very advanced, it's not super complicated, but they tend to jump into it and start doing things, and then they get some result, and then so a lot of time there's some confusion on how to interpret the results. So I hope that this webinar will show very basic but like a foundation of how to use this method. So just a little outline here that we're going to go through. First of all, if we're going to touch on a little bit of the theory of the finite difference time domain method, because I think it's useful to understand what's going on before you start using. And in particular, we'll look at a 2D finite difference. I'll just show some equations and how to set up a mesh for that type of method. And then we'll go on to some boundary conditions that you will commonly use in OptiFDTD and how to properly set them up to do a very simple plane wave propagation. And then the fourth one is going to be very important, because I think this is the discretized Fourier transform and how to understand what's going on. I think actually a lot of people don't exactly understand what it means and how it's calculated. So I'm going to spend some time on that and explain through an example how that works. And then finally, we'll look at a very simple analytic example of total internal reflection rate, how to calculate the critical angle, and how you might set that type of simulation up in FDTD. Now I know this is a very simple example, and it's a lot more simple just to use the Snell's law to calculate this critical angle. But I want to show why when you do an FDTD, the results you get, you might be a little confused about if you don't think about it in great detail. So moving on here, right? So the finite difference time domain. It basically means that it's a simulation that evolves over time. That's the time domain part, and the finite difference is how we approximate the derivatives. You do sort of a central approximation. And the basic equations are the sourceless Maxwell's equations, right? That's on the right side there, with the mu del H delta T is equal to the negative curl of the electric field, and sort of the vice versa for the electric field and the magnetic field. So this will depend on how this equation evolves a field depends on the material properties of the geometry, sort of, that you're simulating, the simulation domain, and that will be the refractive index, or the mu and epsilon. A complex refractive index can sort of be thought of as a absorbing, well, it can be thought of as absorbing material. That's what the conductivity there is, the sigma, next to the E. In a frequency domain technique, you can, say for a certain frequency the loss will be this value, so that's why you can add it into the refractive index. But in a time domain approach, it's actually sort of a separate quantity. So to start off with FDTD, you have to discretize these equations, and so the computer can calculate them. And we're going to go through the 2D type, because in 3D, obviously, the equations are more complicated, and it doesn't. You can look those up in a book or do it yourself, actually, if you'd like to. But I think just to show here what's going on, we can just do a 2D demonstration. So in 2D, there's the added benefit that the Maxwell's equations can be split into two independent polarizations, right? You have TE waves, transverse electric waves, and you can have transverse magnetic waves. This is useful because you can see clearly the effect of how something might affect a polarization in one direction, and instead of how it would affect a different polarization of wave. You can't exactly do this in 3D, though all the components are coupled together through the curl. So you can't actually split the simulation into two types, but in 2D you can. So you can see here that in TE you only have the EY, HX, and HZ components. And if you start with those fields, you'll never excite the other fields. They're not coupled, or they don't, involve the other components at all. In the TM case, you have the HY and the EX and EZ components. And also, just to explain this a little more, our convention for the transverse electric designation might be a bit different than most popular conventions, because we are more interested in guided optics. So our sort of convention stems from that, and is used to describe the input plane polarization. So an input plane by default is in the XY plane in our simulation. So the transverse components are X and Y, and the longitudinal component is the Z. So that's why we have transverse electric wave has EY, and then the HZ components in the longitudinal direction, and the vice versa for TM. That's just some conventions that we should go through, understand it completely. So on to the next slide. So let's look at one of the equations here. I didn't do all of them because it would be sort of a boring exercise, but here we have the equation for the derivative of the electric field in the Y component, and you see it's related to the HX and HZ fields and their derivatives with respect to the Z and X coordinate. And then you have sort of a scaling of the epsilon, or the electric permittivity of the mesh cell. So before we go out, how do we discretize this? Let's look at the grid we would use for a 2D simulation. That's shown on the right there, with the x-axis in the vertical direction and the z-axis in the horizontal. And then the y points towards you or out of the page. So the first thing you do is you'd cut this simulation domain up into equal squares, or rectangles, and then you can set the locations of the field depending on how we're going to discretize that differential equation over there. And you know, in the same simulation domain, you might not have a uniform dielectric. So this is what this sort of blob over here is representing. That's representing some type of other material, perhaps. Maybe it has a different permittivity. So within that shape, your permittivity would have a different value. So in these equations, it would take on the value of whatever that shape has. So moving on here. So right, to discretize this equation up on the top, equation 2, it's a very simple sort of first order approximation of a derivative. You take the field a little bit forward in time, and then you take the field a little bit back in time, or at least the current field, and then you divide that by the change in time. That'll give you a pretty good linear approximation of the derivative with respect to time. Same way, you can find the approximation of the hx with respect to the z coordinate derivative, and also the hz with respect to x. Right? So if we have the hx and hz and all these mesh points over here, if we set it up this way, as in this grid, we can figure out what the EY component is going to be by doing this. We take the higher one and then subtract the lower one, and then divide by the size of that mesh cell, and the same thing with hx. This is a boundary, so it's a little more difficult, but you could see if we chose this cell over here, we could use this one and the other one. And then we can use, if we have an initial condition, we can say, all right, so maybe at the beginning of the simulation, the electric field is 0. So we could say, for the first step, we know it's the EY at the previous time step is going to be 0. And then we can use that to calculate what the new electric field is going to be if we know all the magnetic fields. And then, once, I don't have this equation shown here, but once we know the electric field at a current time step, we can find the magnetic field at the next sort of half time step. So it's very much like a simulation, because you're evolving the field through time, which is somewhat different from frequency domain techniques. This is really, you start off with some distribution of field, usually 0, but then we'll excite some mesh cells or mesh some field with a source, and then we will just evolve it step by step through time. So it's really, the simulation ends when you're done, when you've reached some number of time steps, right? The simulation should keep on going. At some point, the simulation should sort of die down. If you have absorbing boundary conditions, the field should sort of die out. But you could run the simulation for as long as you'd like. So at one point, we have to stop. That's an important concept we'll come back to in the future. And you also see that there's a very big importance on this delta x, delta z, and in 3D you'll have delta y too. That's the size of the mesh. Right? You have to have a certain quality of the mesh, a certain smallness or resolution, so that you'll accurately portray the field. And in future webinars, we'll go over that in detail, or my colleague will. But for now, it's just a good idea to think about, if you have a smaller mesh cell, you're going to get higher resolution. So I want to talk about these two first boundary conditions here, and then I'll show you how to do a very simple plane wave simulation in FDTD. Because you first need to understand these boundary conditions before you can do that. There's 4 main boundary conditions we have in OptiFDTD. The first one is simplest, probably understand. It's the perfect electric conductor. And this boundary condition basically just enforces the fact that any tangential field, electric field, will be forced to 0. And the perpendicular magnetic field will be forced to 0 as well. This is similar to a metal, like a perfect metal. At optical frequencies, metals don't really behave this way, but we could make a fictitious material that does, right? But at microwave frequencies, this is a better sort of approximation to say it's some type of metal. The second boundary condition listed here is the perfect magnetic conductor, and this is a dual of the electric conductor. It'll set the parallel or the tangent magnetic field to 0 and the perpendicular electric field to 0. You can also use these boundary conditions to do sort of symmetric or sort of infinite, depending on your simulation, you can kind of approximate an infinite domain. And that's how we do the plane wave, right? It's similar to in how in electric statics you can instead of having two charges in a symmetric distribution, you can have one and then use a perfect electric conductor to sort of mirror it and then have a smaller problem to solve. It's very similar to that in this FDTD method, and very useful because you can make the simulation domain much smaller. So let's go to FDTD here. I've already got the simulation domain set up. Basically, all I have here, let me just make sure that everyone can see this. Okay, good. Okay. So it's very simple, right? We have an input plane in red here. It's pointing in the right direction. This is the positive z direction. And then vertical, we have our x coordinate, right? And our goal here is to send in a TE wave. And if you remember from our earlier slide, the TE wave, plane wave, should have an EY component, right? And EY is pointing in and out of this plane, which means that the boundary condition at the top and the bottom, we want EY obviously not to be 0, right? We don't want it to be forced to 0 because it's tangential to the boundary, and we don't want that. So we're going to use boundary conditions that are, if I set it up correctly, it should be perfect magnetic conductors, right? I went into the simulation parameters here and set it to perfect magnetic conductor. That'll allow for the EY field to be non-zero, and this wave will propagate properly as a plane wave. So if I just simulate it real quick, this is a very simple simulation, so it takes almost no time at all. I'll just demonstrate clearly what's happening. We're sending in a pulse of a field here, and it's traveling from the left to the right. And then there's some reflection at the end because we're not using, we're using absorbing boundary conditions, but the way this video is set up, it sort of scales the maximum value in the simulation domain to the red color. So even though the reflection is much smaller, we will see that reflection. And I'll show you exactly how large it is in after I talk about absorbing boundaries. Okay, we can do the same thing for the TM wave. This wave has an EX component, and I've already run it. This time, instead of a pulse, you saw how in this one it sort of started at 0, and then a pulse of field travels, and behind it's very low. That's sort of a pulse in time, right? We can also do simulations where the source just turns on and stays on. So I believe this is what this one's set to, right? You just see it's just constantly emitting field here, and it doesn't stop. Again, I'll go over why you might want to use this in a later slide, but just to show you how that would look. And those two videos, maybe I didn't mention it, but those two videos were, of course, of the EY and the EX fields. So let's go back to the slides now, talk about, oops, slides, there we go. And yeah, so I showed sort of how to use those electric magnetic boundaries to set up a plane wave, right? However, if you know about theory, like wave theory or traveling wave theory, how reflections are created, you will know that if you send a plane wave at a electric conductor or a metal, the field will be totally reflected. If it's a perfect conductor, the field will be completely reflected, and none of it will penetrate into the metal. This is not the best for a lot of simulations, right? Because a lot of time you want to send in some type of pulse to sort of probe the properties of some structure that you have. Maybe it's a crystal, maybe it's a waveguide or something like that. And we don't want the wave to interact with the structure, reach the boundary, and then and then reflect and return and sort of mess up the results. We want it to leave once it's done. So in that case, and a lot of the times we'll use the absorbing boundary conditions, and this is implemented through a uniaxial perfectly matched layer type boundary. I'll actually talk about this in a lot more detail in the OptiMode finite element tutorial, the mode solver tutorial webinar, sorry, tomorrow. But it's the same type of method to do it, and there's a lot of ways to think about it. You can think about it of stretching the coordinate through a complex space, which is sort of strange to think about. I like to think about it as this engineered material that you can, it's not very real and you can't actually, well maybe you can create it, but we can't create it presently. It's some fictitious material that is a perfect, it allows you to match the sort of impedance of your simulation domain, and it won't create any reflections. However, once a wave enters this material, it'll start to be absorbed quite quickly. So it's sort of a trick to encase your simulation domain with these materials, so that any wave that touches it or reaches or travels through it will start to be absorbed, and they won't. They have to travel through it twice, right? They have to go one way to reach the end of the simulation domain, and then back to come back if it's going to interact with your simulation domain, and it'll be absorbed in both directions. So you can get a very high absorption of any wave, and so very low reflections from that boundary. And finally, we also have periodic boundary conditions here, and these can be also used to do plane waves. Actually, instead of using those electric magnetic conductors I showed, you could just use periodic boundary conditions, and you can also use it to simulate like unit cells of some type of periodic structure, or so forth. So let's look at. I want to show a little bit more about that reflection that we saw, just to put your mind at ease, to show that it's a very small value. I don't know what happened there. Okay, I hit exit by accident. All right, so let's go and open up this example I have. It's very simple, very similar. I just got to find it. Right, it's a little bit different. I put the plane a little bit farther into the simulation domain, and I have now these two observation points, and these points are going to record the field value at some certain mesh point. Right here, it's in the middle, and as a function of time, right? So we'll be able to see how the field's changing once the simulation is done. So I'll run that. Oh, maybe I should have just used the one I already simulated. While this is going on, I can actually show, if I do it quickly enough, I can actually show the simulation as it's going on. See, this is the pulse of this. This is showing what this mesh point's recording. As the simulation is running, I can see what it's seeing, and it's constantly being updated. It does slow down the simulation, as you can see, so I wouldn't do that for every simulation, just if you want to see quickly if things are working. Okay, so I just wanted to show this real quick. We'll probably have the poll in a few seconds here. I just want to show us right before that. So here is the transmission. I called it the transmission point, at least, right on the right side of this plane, right? So after a few femtoseconds, it starts to see that forward traveling wave here as a function of time, and then you can't see any reflection. We saw in the video that there was, but if I zoom in enough, you will be able to see it right here, right? So this is actually that reflected wave. It's a lot smaller. It's almost 100,000 times smaller, and the amplitude is comparable to the sort of background error. You can see this is sort of non-physical. This is air because of the numerical simulation, and it's on maybe the same order as that, or closer to the background sort of noise and the input pulse. So you can see that these absorbing boundary conditions are quite good at absorbing waves. They're actually especially good at absorbing waves that are perpendicular or traveling straight at them. It gets a little more difficult when they're coming at a glancing angle. So I think this is a good point right now to have a quick poll here, if my colleague can set that up. And I'll have a quick drink of water.
So while this poll is up, guys, if you have any questions, feel free to ask them right now, and Damien can take a look and answer anything that you'd like answered. Again, we're not doing the hands up method with the GoToWebinar interface. Please type the questions in the questions panel on the side, and we'll go ahead and answer any that we can right now.
Okay, I see the poll is settled down here. Nope, it's a few changes. Some people are still getting their last votes in. Right, so if you want to answer this poll, just quickly take your time right now. I'll be starting in about 3 seconds. Count down 3 seconds. Okay. Let me just make sure everyone sees my screen properly. Get a little nervous about that. All right, so let's go back to we just showed that absorbing boundary condition there. And now let's return to the slide because I haven't really explained how these observation objects work. I've shown the observation point, which is fairly simple to understand, I think, but I haven't explained the more sort of useful, well, I don't want to say more useful, but the more used, perhaps, observation type object, which is the observation area, and how that works. So, right, we showed the observation point. It stores the time domain data, right? That graph I had was on the x-axis. It had the time in femtoseconds, and on the y-axis it had the field amplitude in volts per meter. So it's a really sort of clear picture of what's happening at that mesh point. You can also calculate the discretized Fourier transform at a desired frequency from that time domain data. You could put this point, for example, on another side of some scattering object to see how much field amplitude it detects at that point, right? And that's fine, that makes sense. The observation area works in a different way because you don't actually get, we can make those videos, right? We can compress the data and make that video of how the field's propagating through the domain, but we don't actually have a plot of how the field is changing as a function of time. Exactly. We have the video, which is it's got some resolution and it's not perfect and it's only color-based, but we don't actually have a plot of that. Because if you think about it, if we had to have, for each time step, for all those mesh points, a complex field value, I guess it would be real value because it's time domain, but that's, if you do a big simulation, that's a lot of memory that you're going to have stored on your computer, right? Every time step, there might be thousands of time steps, and then your domain size might be 100 by 100, which is 10,000 things, 10,000 elements. So 10,000 by 1,000, that's almost, let me think, it's over 1 million, I think, 10 million. So it's a lot of memory if you want to store all that time domain data. So in fact, we don't do that with the observation area. And I'll go exactly what happens there, but before I do that, I just want to say that we also have this observation line for 2D simulations, and that actually behaves a lot like the observation area, except it's for a line, right? So what do we do to utilize the observation area without time domain data stored? Well, we can actually calculate the DFT as the simulation is going on. And there's options to set those details in the simulation parameters, right? So I think everyone here is hopefully somewhat familiar with the Fourier transform. Basically, we can say that, okay, we have our field up here. It's a function of x, y, z, and t, right, time, and the spatial coordinates. And then we can say, well, we can say that actually it's got some type of harmonic dependence on time, a certain frequency, and the field only really depends on the spatial coordinates, right? That's fine. That's sort of the idea of a Fourier transform. You're going to have yeah. Anyways, it's sort of the idea. I don't want to say it is the idea. In a similar way, and this is important too because we're looking at plane waves again and how it looks like in DFT. If we have, you can also take another coordinate in the space domain and say if it has some type of symmetry, translational symmetry, or you could say that if the material properties aren't changing or independent of this one direction, you can also take it out of the field, like the electric field sort of distribution here, and make it an exponential, right? And this is the idea of having a traveling wave with a certain phase velocity. Now, I probably should have used the more common phase constant here, but I ended up putting e to the minus gamma z, and gamma here is complex, and that's called the propagation constant. So it actually has a real and an imaginary part. The imaginary part is the phase constant, how the phase front changes of the wave, and then the real part would be the sort of attenuation constant. So that's how a plane wave evolves as a function of the direction of its propagation. So how do we calculate this DFT for the observation objects? For the observation point, it's a lot simpler, right? We have all the time domain data at the end of simulation. We can just do a transform right there, right on that. But we don't want to save all that data for the observation area. So at each time step, or it's not exactly at each time step, you can set to be multiple value, like you might skip a couple. But at each step that you set, a contribution will be added to sort of the running Fourier transform, discretized Fourier transform. And that's down here, shown here, right? So we want to get this function of omega, and the analytical way is using the integral. So in a discrete space, we would use this summation over here, where we have the function with respect to time and the current time step n, the frequency at which we want to calculate the transform, and then delta t and j, and then from there, at each time step, we just add another contribution. It's like a running calculation. Obviously, we do it for multiple frequencies, right? Since we're usually exciting it with a pulse, we'll do multiple. We can do it at multiple frequencies. You can set that up again at the beginning of a simulation. And then we'll get the observation object will be showing each frequency's spatial distribution. Or if you had sort of set up the simulation to be a frequency domain, what that steady state or what that final state of the domain is going to look like at a certain frequency. And because this is going to be important so that we understand what it means, I just want to show that a propagating wave like I showed before up here, the gamma z, propagating waves have a linear phase dependence on the propagation direction, right? As z increases, if this was purely imaginary, which it's going to be in the simulation, then the phase of this complex number is going to change linearly with the z direction. And in fact, we can do even better than that. We know it's going to be linear, and we know it's going to be negative. If it's in the z direction, the phase is going to be decreasing, right? So we should see that in our simulation. If we see a plane wave, we should see this linear phase decreasing. And that's a very important subject, or I think it's very important to understand. And I'll talk about this again in the mode solving webinar tomorrow. I'm wondering if I should go to the software now, or I'll quickly explain this right now. Okay, so The input planes and point sources have different options you can check off, right? You can use a modal solution from a waveguide. You can also use a Gaussian type beam. Like this is the spatial, not the picture on the right here. This is sort of the, right, like this optical mode, a Gaussian beam, a rectangular type wave. These ones are used mostly if you have the boundary conditions set up to do a plane wave simulation. Or you can use user-defined. User-defined, you could take this from another simulation. You could create it some other way. It's just a file you load. So that's the spatial dependence. And these pulses can also have time dependence. The most common here is what's called the sign-modulated Gaussian pulse, right? So it has an envelope, this dashed line up here. So it's time and amplitude of the field. It starts off at 0. It's very important that everything starts off at 0. And then it ramps up and follows the envelope of the Gaussian pulse and then ramps back down. The reason why this is so fundamental in FDTD is that if you do the Fourier transform of a Gaussian pulse in time, you'll get a finite width Gaussian pulse in the frequency domain, right? So we'll see this is actually that calculation done on this plot on the right, and this shows you that this pulse has a pretty wide bandwidth. So by doing one time domain simulation, you can get the results for a whole load of frequencies. On the other hand, you can also do a continuous wave simulation, where again it starts. I don't have a picture of this, but it starts off very low, and then maybe I do have a picture. No, I don't. I thought I had maybe. Oh, let me go back here. It starts off very low, and then it ramps up to basically a sinusoid, like a continuous wave laser. It'll just stay at bouncing from 1 to -1 until the simulation stops. This is useful also because it allows the OptiFDTD tool to sort of automatically finalize the simulation, because there'll be some transitional period from when you're ramping up to the continuous wave, like the source to the sinusoid. There's sort of a beginning period, and also it takes time for the field to propagate to all corners of the simulation domain. But after everything is going, it should sort of reach some type of steady state, right? So then the simulation software can figure this out and then stop the simulation once this condition has been reached. However, the problem is you only get the results for one frequency, right? Because it's a continuous wave laser. The spectrum is very tiny. It's focused on one wavelength. Okay, so I think I want to go back to the simulation here and show oh yes, I know what I'm going to do. I just want to show the results of this plane wave simulation, and we'll discuss what it means. Right? So maybe this is not what you were going to expect. It's a very, you could say, boring type plot. Trying to right-click here. Okay. Right? So over here, I had set my input plane. So that's why behind it, it's kind of close to 0. But this is the observation area, what's detected at this frequency, 1.55. So this is the z-coordinate, and then this is the x-coordinate, and then this is sort of the DFT value, the complex field value. And now let's investigate this and see if what we said about plane waves is true. So we excited the wave over here. We saw that in the movie, it had time to propagate all the way to the end. That's good. If we had stopped the simulation before it had finished, before it reached the end of the area, we'd see this kind of ramp down here because the amplitude of the field hadn't really reached that point in the mesh. So this is the amplitude, right? It's a constant value because the field has a constant amplitude, complex amplitude. And now let's look at the phase. Maybe it'll be clear if I do a height plot, but right, we can see that although it's jagged like this because it's bouncing from 2 pi, it's bouncing from 2 pi in the red to 0. It's decreasing, and you can see that it's pretty much exactly linear, right? And maybe I can make it even clearer if I use one of these fancy cuts here, right? The phase is wrapping around because it's going from 0 to 2 pi, but it's decreasing negatively, and it's also linear. So this is clearly demonstrating that this is a plane wave traveling in the right direction at this frequency. If we change the frequency, we should see the slope of the line should change, right? Different wavelength, different frequency, but it should still be linearly decreasing, and it should be a plane wave. So that's really handy. If you ever see something like this where the phase is decreasing linear, and it's got, and in the x in one direction, it's also got a very kind of like a wave front because the phase is all the same in one sort of direction. You really have a pretty good approximation of a plane wave. And that's important for not only this next part of the webinar, but also in the finite element webinar I'll be showing tomorrow. All right, so I'm going to finish off here with a demonstration of how you might do total internal, if you were very extremely lazy, or in fact, it's probably the opposite. If you really wanted to do this the hard way, you'd use FDTD. Again, I don't advise anyone to calculate this by using FDTD. You should do it using, Wikipedia and this answer right here. But it shows sort of maybe results that perhaps you weren't expecting when you run this type of simulation. So, right, total internal reflection is a very fundamental idea in sort of ray optics, rays with sort of phase. I don't know if that's considered wave optics or ray optics, but it's got a very infinitely small width to the ray, so it's a ray. But it's also the idea that they're plane waves and they have some type of phase. So it's a very simple analytic problem, right? You have the input angle θ1 here, you have the refractive index on the left and the right, and you can calculate what the angle is going to be when it passes through. And in the case of if you have a if you're going from a higher index to a lower index, you can get this behavior where the angle, there's a critical angle where if you go past that angle, you'll get total internal reflection. So to set it up in FDTD, all right, how do we approximate a plane wave? We can't use those boundary conditions I showed in the beginning because our wave's going to come in at an angle, right? We don't want to just do a straight perpendicular reflection. We want to see it coming at an angle. So we'll have to kind of try and approximate a plane wave with a wide Gaussian beam. Near the center of the beam, it'll act like a plane wave, but near the edges, it'll do something different. And it also, the whole beam will diverge slowly. And then we have to set up the input and boundary positions. I chose this way. So in the simulation file, you'll see that the input plane's around here, and I'm inputting the beam down here. And then it's going to be pointing in this direction. And that's because I want it to be far away as the boundaries as possible, and I want to get this reflecting behavior. I also want to see if there's any field going through it. And the next point is, should I use a pulse or a Gaussian? And I don't really think it matters, actually. I was thinking about it, and the continuous wave laser might, I think this is a mistake. It should have been Gaussian pulse or continuous wave, actually. But I don't think it really matters because it's not like a frequency-dependent simulation because our refractive indices are constant, and there's no dependence on wavelength here. But they'll give you sort of different results. One will finalize itself once the simulation has reached sort of equilibrium, whereas the Gaussian pulse, you have to set the time step sort of manually. So I don't think it really matters. Maybe there'll be subtle differences in behavior, but I don't think it'll be a big important part of it. So I'll show now how I set it up really quickly. I want to see if I set it up for a failure. 20 degrees. Okay, so this is what it looks like in FDTD. I have this input plane here. I put an observation area around the whole domain, and then this is the boundary. And I have it going from a high index, 2.5, into a lower index of 1. And I can calculate the critical angle there in the PowerPoint. I think I did. I go over here. It should be around 24 degrees where we'll see this behavior. So I do this simulation. Let me just see if I already got one run here. Don't waste too much time. Yeah, okay, so this one was the one done with the 20 degrees, right? So this is not past that critical angle. It's before the critical angle, which means we should not get total internal reflection. So I don't know what you were expecting to see on this plot, but this is what you're going to get. And the reason is we have this Gaussian beam here. It's input to the top right. It's pointing upwards. It's hard to see maybe. Maybe if I'm trying to right click again. This mouse is not very good. It's coming in an upwards direction, hitting this boundary and reflecting. And then some of it is being transmitted, right? So what is this? First of all, what is this weird structure here with all the ripples in it? Well, that's a standing wave, right? If two waves are traveling in opposite directions and they overlap, in a frequency domain, you're going to see this behavior here, which is called a standing wave. So we have like the transmitted beam is sort of interacting with the reflected beam, something you don't get with ray optics because they're infinitely thin. And but we see it quite clearly when we use these Gaussian beams. You also see that the beam is diverging on the right side a bit because it's a Gaussian beam. And let's see if our notion of phase change is proper. Are we doing close to a plane wave simulation? So I switched to phase here, and you'll see that on this side there's an interaction in this area between the reflected and the incident ray or wave beam. But down here we have, it's very close to a plane wave, right? We have this very straight phase or wave front, and it's decreasing linearly in the direction that we told it to, 20 degrees. And on the other side, we also get this nice, in certain areas, like I said, over here it's not so clear it's a plane wave, but in this area at least, it's got a nice straight and it's decreasing linearly the phase. So we can say that's almost like a plane wave traveling from this boundary that way. But over here, of course, it's not so much a plane wave. And now I'll quickly, running out of time here, but I'll quickly see if I can change this to more of a critical behavior. This is the tilting angle here. You start thinking about good questions you might have. The reason we show a lot of 2D simulations live in these webinars is that they can run, quite quickly. The 3D simulations easily can take a couple minutes if they're, to a medium size. And once you try and get into doing a convergence analysis, it can take hours and even days. So here I increased that angle there and went past the critical angle. And now we see it's almost completely reflecting off this boundary, right? We get a little bit of this penetration into the secondary material here, but by far most of it is reflecting. And you can think about this as sort of an evanescent decaying wave, right? It's almost like a waveguide mode, right? The core doesn't confine the light entirely. Some of the wave is decaying in the cladding. So I think I wanted this to show that, okay, it's a very simple analytic problem. You want to do total internal reflection, that's great. But when you use FDTD, you might not get exactly what you expect in the results. But I hopefully during this presentation, I explained how the observation areas work, what exactly that DFT means. And so in the later, more advanced webinars that we're going to have this week, you'll be able to understand it much more clearly, or at least it won't be totally new to you. So I'd like to open up the floor now to any questions you have, right? This is the question period. Feel free to ask them in the questions box, and we're going to have a poll start now as well.
And just to wrap everything up, guys, so we do have webinars all week, as most of you know. They're basically going at 9 a.m., 11 a.m., 1 p.m., and 3 p.m. Eastern Standard Time, so that's GMT -4. Feel free to keep on registering for as many as you'd like. We do have quite a bit of space now that we have upgraded our service. So we're going to be choosing we're going to be putting together the approved list for the draw. So as described at the beginning, you basically have to be present for all 3 polls, and then you get thrown into the $50 draw. You should see the results for that on the website in about 10 minutes. Again, I put the link in as in the chat message to everybody, so you can click on that link. If anybody has any questions that they want to ask directly to us afterwards, you can email them to support@optiwave.com, or if you have a quotation that you'd like drawn up for yourself, feel free to email info@optiwave.com. So I'm going to close the poll now, and if there's any questions, which I don't see any right now, we're going to go ahead and just close off the session.
We got one question here, not so much about theory or anything like that, but the question is, can we have the webinar videos? And yes, if you've registered for this webinar, we'll be sending out an email with a link to that at some point in time. Not sure exactly when, but yeah, they'll be available to watch.
The webinar videos will come out exactly 24 hours from when we stop the webinar, so you'll get it tomorrow at 10 a.m. Eastern Standard Time. There's a couple other questions. I'll let Damien go ahead and read through them, and we'll answer as many as we can right now. Otherwise, we'll just handle some of the more in-depth ones afterwards.
So one question we have here is, can we model a silicon-based optical modulator? And the answer is, depends what you want to model. We have, we can do the optics part. You can simulate the behavior of how the wave will travel through the modulator, how small changes in the refractive index might affect that wave. We can do that type of thing. Another question we got here is, are we going to have some book published on the FDTD? I think is a question to understand the software, I'm assuming. And yes, we do. The software comes with a manual, right, a PDF, and our website has some useful information on it as well. So if you have any questions, you can always check those sources, the manual and the user reference. There's some questions about the material models that we can do. And we'll actually have, if you're interested in what kind of materials we can model and how we do it, there's going to be an interesting webinar either today or tomorrow about our Lorentz-Drude fitting algorithm that we've implemented. So you can take your own sample data and then fit that to a Lorentz-Drude model. So you'll be able to model more complex materials from an experimentally gathered source of data.
I think this might be a good point to end the session. Damien, do you have any other questions you want to answer right now, or? Okay, I think we're going to go ahead and end the session. Thanks everybody for attending, and again, we have another session on one of our other products starting in 1 hour, so feel free to click the webinar week link and check out all the other sessions and sign up for the ones that you'd like. Thank you very much.